Okay, so here's class 21, the lecture portion of this. I know we already went over this today, but figured I'd put together a video just to summarize it for posterity, and maybe if you wanted to revisit this. So we're doing kinetics of rigid bodies again for class 21. Same topic as class 20, but we're going to maybe focus on this constrained plane motion kind of idea. We put up this equation right here, but I think it would be better to use this as a concept, right? So this equation right here is the most generalized, where we have some arbitrary point O that we're going to use as the reference. Instead of taking it about the center of gravity and therefore also having the moment of inertia be about the center of gravity, we could take it about any point. And now, to be able to keep it generalized, we call it about the effective moment. The effective inertial moment is what we mean. And then we can take into account not only the mass moment of inertia times alpha, but also the mass times acceleration as an inertial force times the moment arm about the point about which that it's moving, right? So the mass times acceleration, that's referring to the acceleration at the center of gravity. And so if we take a position vector, it's going to end up being perpendicular to that acceleration and will act like a moment arm for that inertial force. And now we take this special case here of constrained plane motion, right? So this is not a generalized form. We know that the general formula is going to be this right here, right? Let's see. Why did I do that for? And when we have, for this effective moment, that is, just as I described, going to be mass times acceleration times the distance from the center of the mass to the point about which that we're moving, right? So that O, right? It's only for the constrained case, though. When something is pinned about a point, this does not apply. What happens now does not apply to any other condition. So we take the FBD and the IBD, and we take the sum of the moments as what I've written up right above. And on the left-hand side, that's as you would expect to get all those and take it about referencing point O. But now on the right-hand side, we take that mass moment of inertia about the center of mass times the alpha, the angular acceleration, but also, so that's an inertial rotational moment, right? An inertial moment. But now we also are going to have, because we're taking it about O instead of taking it about the center of gravity, we will have to have mass times the acceleration at the center of gravity, but only the tangential component, because the normal component is passing through the point that we care about, right? So that mass, so it's only going to be the tangential component, and the distance from that center of gravity to the point that we're rotating about, this R, we could say that it's G with respect to O, right? But we also know from kinematics, when we have this pinned type of arrangement here, that the tangential acceleration at G with respect to O is going to be alpha times RG with respect to O. So we can replace that. And so we have two RGs with respect to O. And what we're left with now, when we move alpha to the outside, is the parallel axis theorem. And what we've essentially done is we've proven the parallel axis theorem to be true, and we've shifted the mass moment of inertia to be about the point O. So we can have a simple but equation for this condition. But remember, this is only applicable for this type of motion that's pinned. And So here is the type of problem that we're referring to, and here is the FBD and IBD, or ID as we're calling it, inertial diagram. And this is the general case, right? That what we're talking about is that we would have a mass times acceleration at the center, and then also have an I about the center as well, and alpha, right? And one thing you should do, if we're going to do the effective method, right? So this right here is some of the moments about A. We still need to take it about A because we want to get rid of those reaction forces, is going to be equal to the sum of the moments about A, the inertial effective part. We had alternative, and by the way, if we do this, right, and you do pick an AC, make sure you're picking your AC so that it will agree with the direction that you choose for your angular acceleration. You will get a wrong answer if those two things don't agree with each other. But you can by observation you could see what direction the acceleration of C needs to go. Alternatively, we could just simply write IA alpha right there, right? And so that's that is a different alternative equation. Sum of the moments about A is equal to IA alpha, right? Two different techniques to do the same thing. It's easy to fall into the trap of using this all the time. So we'll do some examples. These are examples. This is an example out of the book right here. I'm not going to go through this one. You could read this yourself. I don't really like the way that I like the way the book does it, but I don't quite like the way this particular example walks through it. But yeah, definitely look at this and try to interpret it here for that sample problem. But I'm going to do this example next in a separate video.